Hi, my name is Corinne Stucker and I'm happy to present our work, ImpliCity, city modeling from satellite images with deep implicit occupancy fields. This is a joint work with Benjin Ke, Yuanwen Yu, Shenyu Yuan, Iro Armeni, and Konrad Schindler. Typically, satellite-based 3D reconstruction pipelines adopt stereo matching algorithms originally developed for terrestrial or airborne photogrammetry. The principle of such algorithms is to find a dense set of image correspondences that have a high photo consistency while at the same time enforcing piecewise smooth surfaces. After matching all suitable image pairs, the correspondences are triangulated to 3D points and fused into a single point cloud. The point cloud is then converted into a digital surface model, typically parameterized as a regular 2D elevation map. Due to the limited image resolution, the suboptimal stereogeometry and radiometric differences caused by variable lighting and atmospheric effects, digital surface models derived from satellite observations tend to be noisy, lack sharp geometric features, and often do not attain the accuracy needed for high-resolution applications such as 3D city modeling. Recent works have proposed to complement classical stereo algorithms with a subsequent learned refinement step to restore shape regularities, complete missing surface details, and remove noise from the imperfect digital surface model. These learned refinement approaches improve the reconstruction quality significantly, but they cannot represent arbitrary topologies and are inherently limited in their ability to resolve small structures. Furthermore, they tend to miss small geometric features that are clearly visible in the images. We argue that the reason for the limited quality may be a too early heuristic reduction of the point cloud to an explicit 2D elevation map and the discretization of the elevation map itself. Hence, the idea of our work is twofold. First, we introduce ImpliCity, a coordinate-based neural representation which models the 3D scene geometry as an implicit continuous occupancy field. Second, we refrained from parameterizing the initial reconstruction as a 2D elevation map and instead revert to the raw, irregular, and unoriented point cloud. Since this point cloud does not preserve fine-grained geometric details that are, in principle, visible in the images, we leverage two ortho images as additional input to our network. In this way, we constrain the network to reconstruct crisp crease edges and height discontinuities that are aligned with the image gradients. We show that this approach enables the extraction of high-quality surface models that feature minute shape details, smooth surfaces, and crisp building edges. The reconstruction is effective and applicable to large-scale scenes. We model the scene geometry as an implicit continuous field of occupancy values. The field is represented by a function f that, for a given 3D point x, returns the probability that the point is occupied. Hence, the function should return 0 wherever there is free space, and 1 if the 3D point is on or underneath the surface. In our case, we also pass two location-dependent latent codes to the function to modulate the occupancy probability. The first latent code describes the local structure of the point cloud, and the second latent code encodes the local satellite image content. We parameterize the function f and both feature extractors as neural networks. Ultimately, we compute an explicit representation of the surface by sampling a sufficiently dense set of 3D locations, evaluating the function f at all of them, and extracting the isosurface with f equal to 0.5. Implicit representations have been explored to model the 3D geometry of local shapes, single objects, indoor scenes, and single buildings. In this work, we go one step further and investigate their potential to reconstruct large-scale urban scenes from satellite data. Our network takes the point cloud and the two ortho-photos as input and transforms them into a shape embedding and an image embedding. The shape embedding encodes the local 3D context for which we adopt a single plane encoder of convolutional occupancy networks. The image embedding is generated by the pixel-aligned encoder of PyFu and is used to encourage consistency between the reprojected 3D scene geometry and the image content. With these embeddings, we can, at any query point x, read out the associated shape and image latent codes and pass them, together with the coordinates of the query point, to a shallow MLP, The MLP is trained to estimate the occupancy probability of the query point. At test time, we then extract an explicit surface representation from the implicit occupancy field and parameterize it as a 2D elevation map to ease direct comparison with competing baselines. An alternative interpretation of our method is a deep implicit representation of surface geometry guided by 2 ortho-photos to retrieve high-frequency details. This raises the question whether a single ortho-photo might be enough and whether the use of images improves the reconstruction at all. To investigate these questions, we start from our full model based on stereo guidance, which we refer to as ImpliCity stereo. We then construct several network variants that ignore some of the input data but are otherwise identical. The first variant, ImpliCity mono, uses a single ortho image to generate the image embedding. The second variant, ImpliCity zero, has no access to image information and merely learns the mapping from 3D points to occupancies without conditioning on any image evidence. We evaluate our method on panchromatic worldview 2 and worldview 3 satellite images acquired over Zurich. To generate the input point cloud, we use a re-implementation of state-of-the-art hierarchical semi-global matching tailored to satellite images. To train our method, we need to know the true occupancy of any 3D spatial location. We derive this full 3D supervision from the city model of Zurich. We randomly sample points in free space and in the vicinity of roofs, facades, and terrain, and assign true occupancies to the sampled points, depending on whether they lie above or below the surface. We then train ImpliCity by minimizing the binary cross-entropy loss between predicted and true occupancies. We first assess the performance of ImpliCity zero so as to quantify the impact of implicit neural modeling in isolation without image guidance. It turns out that mapping the point cloud to a deep implicit representation and then extracting an explicit elevation map from that intermediate representation performs a lot better than rasterizing the point cloud directly via a conventional heuristic procedure. Quantitatively, ImpliCity zero improves the mean absolute error by more than 50% compared to the conventional stereo pipeline. ImpliCity zero also outperforms ResDef0, a method that directly refines the conventional elevation map by regressing an additive height correction at every pixel via a standard unit. When using additional monocular or stereo information to support the reconstruction, we observe the same trend for ResDef and ImpliCity. The variants using a single image outperform their respective counterparts without image guidance, and stereo-enabled variants bring another improvement compared to the monocular versions. We report the lowest reconstruction error for our full model based on stereo guidance, which achieves a mean absolute error of 1.5 meter. When comparing the results visually, we observe that the reconstruction generated with ImpliCity zero exhibits markedly less surface noise than the conventional reconstruction. Furthermore, ImpliCity zero separates build-up areas into plausible individual units and reconstructs sharp building edges, gable roofs, and even buildings that are hardly recovered in the conventional reconstruction. ImpliCity mono reconstructs buildings that have been missed previously, sharpens and straightens building outlines, and partially recovers geometric details on roofs. Finally, ImpliCity stereo further improves the reconstruction. Buildings have exceptionally crisp and straight outlines, and there are fewer implausible bumps on the terrain. Most striking, ImpliCity stereo is the sole method that recovers fine-grained roof structures such as dormers. To summarize, we have presented ImpliCity, a neural representation of the 3D scene as an implicit continuous occupancy field driven by learned embeddings of the point cloud and a stereo pair of ortho-photos. We have shown that this representation enables the extraction of high-quality surface models from satellite data. For additional details and results, please check out our paper and supplementary. Thank you for watching.